variance, the other feature we're interested in when we're looking at this stuff. So x is our discrete random variable, whatever it's measuring. So the variance of x is defined like so. The sum of x minus mu, now remember mu was the mean, or the arithmetic mean, but also the expected value, whichever way you want to call it, squared times the probability of x. Okay. So again, so px represents the probability of x equaling x. Mu is the expected value. Now, that x minus mu is basically what we call the deviation, because we're saying, well, how far away from the mean is this particular result? So x minus mu we call the deviation. So it means variation is a measure of spread. So yesterday, our expected value was a measure of the centre of the data. Variance is a measure of the spread of the data. So let's use the same example from yesterday. So our milk marketing survey, there's where we were at yesterday. We had our probability of x, but then our xpx, so we could work out expected value. 2.2, that was our expected value, so that is mu that we'll use when we sub into this row, x minus mu squared. So I'm going to need to know that because I want to multiply x minus mu squared by the probability of x. So now I'll create another row, x minus mu squared times the probability of x. And so 121 on 25 times 2 on 25. So there's my 242 on 625, and so on and so on and so on. But there's the sum at the end that I'm looking for, the variance. So remember, the variance of x we said was the sum of that bottom row there, that x minus mu squared times the probability of x. So 1.52 is the variance. There is, I think, an easier way of doing that, because remembering all that, I think, can be tricky. I think a nicer way of doing it is this, and if I play around with the variance of x, so it's the sum of x minus mu squared times the probability of x. Now if I use my laws of expectation, that's why I needed to show you those yesterday so I could play around with this. I could say, well hang on, that's the same as the expected value of x minus mu squared, because I'm saying it's x or something times probability of x. And that was the expected value of that thing. Remember the definition, I'll just go back. Here we go. X times px, the sum of that was our expected value. So we have something times px, sum of it. So we've got the expected value of x minus mu squared. Well, x minus mu squared, if I expand it out, is x squared minus 2 mu x plus mu squared, which then I'll just separate because our law of expectation, remember we said if we had two events, we said the expectation of x plus y was the expectation of x plus the expectation of y. So that's what I've done there. I've split it up into three things. Now, the last one I haven't said the expected value because mu squared would just be a constant. Remember, mu is the average. So what would you expect this constant value to be? Well, I'd expect it to be the constant value. So I've already worked out that's mu squared. So with the expected value of x squared minus 2 mu times the expected value of x, well, the expected value of x is mu. So I now have 2 mu times mu, and I get this much nicer formula. To work out the variance, it's the expected value of x squared minus the mean squared. Okay? And so expected value of x squared would be x squared times probability of x. It makes my distribution table a lot easier because the rows now fall logically. The first row, probability of x. The second row, x times the probability of x. Oh, sorry, and remember that's mu. Third row, x squared times the probability of x. So it's a very natural flow for each row. And I want the sum of that row, so 6.36. That is the expected value of x squared. So it's not the answer for my variance, it's the expected value of x squared. But I know the variance will be the expected value of x squared minus mu squared. So if I sub that in, I'll get 6.36 minus the 2.2 squared, and I come up with that same answer of 1.52. As I say, I think from a logical setting out point of view, that's a lot nicer than, let's just go back to it, than that one. Try and remember, oh yeah, I need this row x minus mu squared, then it's going to be x minus mu squared times px. I just find that messy. It's your choice, of course, how you do it. But as I personally think, let's get to it. There we go. I personally think that's an easier way of working out our variance. Which brings us to something you have heard of before, standard deviation, which is symbolised with a lowercase sigma. Now, why do we need standard deviation? Because we've talked about deviation variance, but if you look at the units, if the random variable x is measured in units, then what I've just worked out, it's the expected value of x squared minus the average squared. The units must become units squared. So for a sake of comparison, it's really hard. I've got one thing that's in units squared, I've got one thing that's in units. And so standard deviation just turns it into the same units. So all we do is that. Oh well, we find the square root of the variation. Now I know in the junior years there's this wonderful formula that they give you to find the standard deviation. Do you recall it? If anyone remembers it, I'll be amazed. But it's a horrible formula. There's the sum of the square root of it, all this, that and the other. And most of the time people just go, oh, just use my calculator. It's just easy to bung the numbers in and work it out. But by using variance, we can find the standard deviation quite quickly. Because again, I go back to our table. The table is quite logical. So if I want to work out the standard deviation, I find the variance, and then standard deviation is just the square root of that. So for our example, square root of 1.52, so the two decimal places, the standard deviation is 1.23. And that's now in the same units. So remember, our example we were talking about was the number of litres consumed. So we're saying on average, it'll be 2.2 litres. But the deviation, so to get an idea of spread, would be 1.23 litres. This now brings me to something called standardising the data. Now, you might have heard the term standardising before. They do it to HSC marks, they do it to all sorts of things, but I use it because basically those Z-scores are standardising the data. So you can compare sets of data reasonably fairly because you convert everything to the same average or the same deviation. So the original data, by the way, don't panic too much about how I get this, because I don't think we're going to be asked how you get this. But just to show you where it comes from, we're not just pulling it out of thin air. Expected value is mu, and we just said the variation then is the standard deviation squared. So that's our standard piece of data. Now, in some non-mathematical subjects, and you might have seen some teachers do this, they say, oh, geez, these marks are a bit low. Don't worry, we're going to scale them. They use the word scale. We're going to scale them. Oh, yeah, how are you going to do that? Oh, we'll just add 10 to everyone. It's not scaling. It is sort of standardising, but it's a very poor way of standardising. Because let's see what happens. If I'm just going to add a constant amount to each piece of data. So my new random variable y will be defined as random variable x, but we're just going to add a constant value to every result. So the expected value of y will be the expected value of x plus c, which I can break up into the expected value of x plus the expected value of c. So all I've done, the average, as you would expect, if I've just added a constant amount to every piece of data, you'd expect the average to go up by that constant amount. So okay, we've altered the average. But what have we done with the spread of the data? So now I want to find the variance of x plus a constant. Now, using our formula, that'll be the expected value of x plus a constant squared minus mu plus a constant squared. If I expand both of those out, so the expected value of x squared plus 2cx plus c squared minus mu squared minus 2c mu plus c squared. Now let's play around with that expected value. and I'll break each of those up into 3 expected values. Expected value of x squared, 2c is a constant, I can bring that to the front, so 2c expected value of x. C squared is a constant, so what would you expect for a constant? Well, you get the constant, c squared. We can see there's some cancelling there that's going to happen, c squared minus c squared. But the expected value of x we know is mu, so I can sub that in. So I now have, when we tidy all that up, the expected value of x squared minus mu squared. Well, that's just a variation of x. And so what have we done? Absolutely nothing. We have not changed the spread at all. So simply adding amounts, it doesn't change the shape of the data. If I think of the graph, if that was, say, all the original points, all we've really done is shifted the curve and we've moved the average up. It does nothing with the spread. Okay, so if they're saying, oh, this is a really hard test and so we're going to add 10 to everyone, that person who might have been, oh, I don't know, 40 marks behind someone else is still going to be 40 marks behind someone else. It hasn't changed. It's not really scaling. It is a form of standardising, but probably not a great way of doing it. But that's what non-mathematical people do. They don't understand that, so that's what they do. A different way of doing it would be, instead of adding by a constant amount, we'll divide by a constant amount. So what would happen there? So now I'm going to define a new random variable z. So the expected value of z would be the expected value of x divided by k. And the variance of z will be the variance of x divided by k. Well, expected value of x divided by k, again, k is a constant. So it's like I'm saying I'm going to factorise out the 1 on k. So the expected value of x over k, we know the expected value of x is mu divided by k. Again, that's logical. If I'm going to divide every piece of data by k, then the average should be divided by k. Makes sense. But now the deviation will change as well. Because over here we'll go, okay, by that definition, we get the expected value of x on k all squared minus mu on k all squared. Expected value, well, the k squared I can pull out, it's a constant. So I've got the expected value of x squared on k squared minus mu squared on k squared. Treat it all as one fraction, common denominator k squared. Expected value of x squared is the variance. Expected value of x squared minus mu squared is the variance. And so there we go. We've got sigma squared on k squared. So the deviation has also been divided by k. So we've affected both. Not only have we moved the graph to where we want it to be, but we've changed the shape of the data as well. And whatever k is, we can make it narrower and make the scores closer together, or I could make it wider. It just depends what value of k I pick. So dividing it by a constant amount changes the shape of data as well as altering the mean. So from a graph point of view, if that was the original data, then I'd be shifting it, u divided by k. I'm assuming k is a number bigger than 1 here, so it makes it smaller. But then I've also made it narrower. The deviation is less of a spread. That's probably a better way of doing it, which is where we get z-scores from. Because when I work out your z-scores, I what's called normalise the data. And there's the formula that I use. Right? It's very simple. Not only do I add a constant amount, or well, in this case subtract a constant amount, I subtract the average, I also divide it by a constant amount, that deviation. Why do we do it that way? Well, again, let's see what happens. So the expected value of z here be expected value of x minus mu on sigma. Sigma is the constant, so I can pull it out. Expected value of x minus mu on sigma, which will be mu minus mu on sigma, 0. It sets the average at 0. So that's why we do that bit. The variation, what happens? So I'll get the variation of x minus mu on sigma. So again, sigma squared gets pulled out as a constant, and we get 1. And so it sets a very nice set of data where the average is simply 0 and the standard deviation is 1. do not panic. You don't have to work on that. I'm just showing you the mathematics behind what we're doing there. But that's why we're interested in expected values and variations for being able to read the data effectively. So 13C, let's add that to our questions, and we'll have a variation of a day.